Number 28, and we are going to solve problem number 170 from chapter 7. So as given in the problem, we are given a hollow beam which is completely submerged in the fluid of unit weight rho 0. The thickness of the surface of the beam is T and the width of the beam on all the four surfaces is B. The beam is completely submerged in the fluid, and this is our reference point. This is our x2 direction and this is our x1 direction. There are three parts of solution to this problem. First, we are asked to plot the traction field over the surface of the beam. Second, we are asked to find the resultant applied force on the beam. And third, we are asked to find the moment on the beam. We will start by finding the surface normal. We'll first start by plotting the traction on the surfaces. On surface 1, our traction will be in the direction opposing to x1. On surface 2, our traction will be in the direction opposing x2. And on surface 3, our traction will be in the direction of x1. And there is no traction on surface 4 by definition. Now we will go to find the surface normal. The surface normal on surface 1 will be opposite to the traction plot. So N1 is equal to E1. Since our normal will be opposite to the traction, it will be in the direction of x1. So N1 is equal to E1. And the pressure for surface 1 will be rho 0 times x2. Rho 0 is the unit weight of the fluid, and as the weight increases as we go deep down towards x2, the pressure becomes rho 0 x2. Similarly, we get the normal and the pressure for surface 2 and surface 3. There will be no pressure on surface 4 because it's at the top and it corresponds to the reference point, which is 0, 0. Now we will find the traction, which is equal to S times N1. But S over here is the pressure, is the stress tensor, which is opposite to the pressure. S is equal to negative Pi, and the body force B is rho B times E2. Rho B is the unit weight of the surface of the beam, and it's in the direction E2. Now direction 1 again is equal to S N1. So as we are defined S and N1, we get result equal to negative rho 0 x2 E1. Similarly, we get the result for surface 2 and surface 3. Now we will go to the definition of the resultant applied force. Resultant applied force is the traction over the surface of the beam plus the body force over the area of the beam. First, we will just find out the traction over the surface of the beam. So each of our surfaces 1, 2, and 3, 4 are of the same width b. So our integrals will be from 0 to b in each surface. So for surface 1, it will be integral 0 to b, traction 1 in the direction x2, since our traction plot is in the direction x2. Similarly, we get the integrals for surface 2 and surface 3. Solving the above integrals, we get negative rho 0 b squared E2. So we have solved the first part of the resultant applied force. Now we will go for solving the body force over the area of the beam. To solve that, let me explain a figure over here. We will need to double integrate in the direction x1 and x2 for each surface. Let's take an example for surface 1. The thickness for surface 1 is T. So this point over here, which will be B minus T, and the end point over here will be B in the direction x1. Similarly, in the direction x2, it will start from 0 and go to the width of the beam, which is B. So our integral for surface 1 becomes in the direction x1, it will be from B minus T to B, which is as here, and in the direction x2, it will be from 0 to B, which is over here. So this is how we get the integral for surface 1. Similarly, we get the integrals for surface 2, surface 3, and surface 4. Solving the above integrals, we get 4 rho b t b minus t E2. So this is our solution for the resultant applied force simplified and combined both the body force and the traction. Now we will go to find the moment for the beam. So this, similarly to our above figures, these are our surfaces 1, 2, 3, and 4. Each one of the surface have equal width, and this is our position vector. The position vector P, the general form is x1e1 plus x2e2. Now, the position vector for surface 1 will be B in the direction x1, so it should be BE1 and plus x2e2, which becomes position vector is BE1 plus x2e2 cross the traction 1 on surface 1. Traction on surface 1 we have already defined earlier. So our position vector cross the traction on surface 1, the ultimate result becomes rho 0 x2 square e3. Similarly, we find the position vectors for surface 2, 3, and 4, which are displayed here, and we get the following results. Now, the second part to our solution, which is position vector times the body force over the area. So our P cross V will be, again, we have defined the P on each surface in our part 1 solution as seen here, and our body force as defined earlier it was rho B E2 in the direction E2. So solving this cross product, we get like this solution for surface 1, 2, 3, and 4. Now the definition for moment is position vector cross the traction on surface plus the position vector times the body force over the area on the beam. So first we will just find the position vector cross the traction on our surface. So for surface 1, again the width runs from 0 to b, so integral becomes 0 to b, and the cross product was rho 0 x2 square e3 in the direction x2. Similarly, we get integrals for surface 2 and surface 3. Since the cross product of surface 4 is 0, we will just write 0 for surface 4. So solving this above integral, we'll get minus rho 0 b cube over 2 in the direction e3. Now we will go to find the second part of the moment, which will be integral on the area position vector cross the body force. So as defined the limits earlier, on surface 1, the cross product of position vector times the cross the body force, the result will be rho b x1 e3, and the integral is applied in the direction x1 and x2. So we get this result for surface 1. Similarly, if we apply the double integrals over surface 2, surface 3, and surface 4, we get the following results. On surface 3, the result is 0 because the cross product on surface 3 of P cross body force is equal to 0. So this is our result for the integral on the area of position vector cross the body force. So combining our both the results, one for the position vector cross the traction and one for the position vector cross the body force, we get this ultimate result for the moment. Thank you.